All right, so a lot of you told me that you really liked when I made videos covering your note information. So while I still want you to watch the other videos assigned to going over our topics this unit, because I do find that they have a lot of value, and there's things that they do in those YouTube videos that I can't do that are more interactive or maybe demonstrate a process. I've heard that you do like when I go over these as being helpful for our practice problems. So let's talk about what most chemists call an ice chart or a rice table. And what it is this is a tool for helping us solve equilibrium problems. It allows us to look at initial conditions and find out equilibrium conditions by looking at how it changes in the process. So let's start with a really generic sample to get an idea of how a rice table or ice chart works. If we have the reaction in which A and 2B, both gases, are in a reversible reaction with C and 2D, also gases, then what we can ask ourselves, we're given 3 moles of A and 4 moles of B. When they react, 2 moles of D are produced at equilibrium. Let's start by figuring out what the equilibrium constant is for this. So given this information, what is the equilibrium constant? Well, we're going to make our rice table. R is rewriting our reaction. The states are really important. As we know in equilibrium, we're only interested in essentially non-solid, non-liquid states. So I'm going to write A, 2B, reversible with C and 2D. And then I'm going to divide up my chart. So there's R. I is our initial concentration, so what we're starting with. C is how we're changing. And E is our equilibrium concentrations. So I is initial concentration, E is equilibrium concentration, C is how those are changing in the process. And I'm going to go ahead and finish drawing in my chart. So here's my chart. I'm going to fill in what I know, given 3 moles of A and 4 moles of B. So that's our initial concentrations. We have 3 of A and 4 of B. And we're told they react to form 2 moles of D. That means at equilibrium, we have 2 moles of D. So now let's start filling in our chart. Well, given 3 moles of A and 4 moles of B, that means I did not yet have any products initially. So 0C and 0D. Now what I want to do is figure out how things have changed. Well, I started with 0 initially, and I ended with 2 moles finally. So that means the change was an addition of 2 moles. If one product went up, the other product went up. If the products increased, that means our reactants decreased. Now let's start using what we know about D to figure out proportionally the rest. Notice there's a coefficient of 2 for the D, and there's a change of 2. Well, what's our ratio between D and C? For every 2D, there's 1 C. So if D increased by 2 moles, C will increase by 1 mole. If D increased by 2 and B has a coefficient of 2, so in there a 2 to 2 or 1 to 1 ratio, then that means B would have decreased by 2. If D has a coefficient of 2 and A has a coefficient of 1, again, a 2 to 1 ratio, if D increased by 2, A would decrease by 1. So we use our coefficients in that mole ratio to extrapolate from the data we know. Now, we go down, so 0 plus 2 is 2 moles of D. For C, 0 plus 1, that's 1 mole of C. 4 minus 2 is 2 moles of B, and is 2 moles of A. So our rice table helped us figure out our ending concentrations, or our concentrations at equilibrium. Why is it important to know our concentrations at equilibrium? Well, the question is asking us to find the equilibrium constant. Equilibrium constant, which we wrote before, is the concentration of the products raised to their coefficients over the concentration of the reactants raised to their coefficients. And I actually now know the equilibrium concentrations, so I can plug all of these in to my formula. So I get 1 times 2 squared over 2 times 2 squared. And then I'm just going to do this on my calculator, order of operations. I'm going to make sure to square the 2 first and multiply by 1, divided by 2 squared multiplied by 2. And I get our equilibrium constant is 0.5. And remember, this is a unit-free number. All right, so that's a generic sample. Let's go ahead and look at an example with actual elements instead of made-up elements. I would recommend go ahead and pause the video now and try this on your own, then hit resume or play to see how we solve it together. Okay, hopefully you're ready to check your answer. Let's go through this. So the initial concentration of our HI, hydriodic acid, was 0.05 atmospheres. So notice this isn't concentration, it's a pressure, but that's okay, that works as well. Calculate the equilibrium constant if the hydriodic acid was reduced by 0.02 atmospheres. So I'm going to set up my rice table again. So RICE. I'm going to write in my reaction, hydrogen and iodine in a reversible reaction with hydriodic. And then what do I know? Well, my initial concentration was 0.05 atmospheres. And it was reduced, or my change was 0.02. So now that's what I know. The first thing I'm going to do is figure out my equilibrium concentration, or in this case, pressure of the HI. That's going to be 0.03. I can assume that if I had 0.05 of the HI, I did not have any hydrogen or iodine gas initially. I can figure out if my product was reduced, that my reactants increased. You can't go anywhere from 0 but up. And again, I can use the coefficients to set up a mole ratio. So if it's 0.02, coefficient of 2, coefficient of 1, coefficient of 1, then that's going to be 0.01 and 0.01, because we have a 2-to-1 ratio of our product to both of our reactants. So what's 0 plus 0.01? 0.01 and 0.01. Once we know our equilibrium line, we can set up our equilibrium expression, which is the concentration or the pressure of the products over the concentration or the pressure of the reactants raised to their coefficients. I plug in my equilibrium values. So I have 0.03 squared over 0.01 times 0.01. And I get our equilibrium constant for this reaction is 9. All right, I hope that that agrees with the work you tried. Let's do one more example. For this example, what I want to look at is, let's see, actually, let's do this. If you want to practice one more example, go ahead and pause the video and try this one. This is a lot like the previous ones we've done. I'm going to go through this one really quickly because I want to get to my last example, which is a little different than the ones we've done up to here. So let me go ahead and go through what we're doing here. We have our reaction 2A plus 4B in a reversible reaction with C and 3D and 3E. Initial change equilibrium. Set up my chart. All our basic steps. What do we know? We were given 7.5 moles of A, 5 moles of B, no products yet. At equilibrium, only 6.5 moles of A remained. That's a change of 1. If A went down, B must have also gone down, using up those reactants to form or gain our products. Use our mole ratio to extrapolate. Between A and B, that's a 2 to 4 or 1 to 2 ratio, so we're going to lose 2. 2A to 1C, that's a 2 to 1 ratio, so that's going to be 0.5. 2A to 3D, that's a 2 to 3 ratio, or to make it easier, I can compare C and D. C is a 1 to 3 ratio, so that's 0.5 times 3, or 1.5. And same, C to E is a 1 to 3 ratio, or 3 times larger than what C is, so 1.5 molarity increase. Go through and finish filling out our equilibrium values. We have 3 moles of B, 0.5 moles of C, 1.5 moles of D, and 1.5 moles of E. Set up our equilibrium expression so that we can find the constant. That's concentration of C times concentration of D cubed times E cubed all over A squared times B to the 4th. Plugging in what we know for our equilibrium concentrations. And just remember, it's really important to preserve order of operations. You know, I'm a huge advocate of using tons of parentheses on your calculator just to make sure it really gets the order of operations correct. And once we get this, we have 1.5 cubed times 1.5 cubed times 0.5 divided by 6.5 squared and 3 raised to the 4th. Our answer is going to be 0.0016. Whoops. Ran out of space to write. Let's go ahead and move down a line so I don't accidentally press buttons on here. So 0.00166. Remember, these are unit-free numbers. All right, so we've practiced a bunch where we're determining the equilibrium concentrations and then using that to find the constant. Our last example, what's going to be different about this one is that we're given initial concentrations. We're looking to determine the final concentration given the equilibrium constant. So instead of solving for the equilibrium constant, now we have it, and we're going to use that to find final concentration. So let me show you how this one's different. I'm going to set up my rice table again. So here's my rice table. First thing I'm going to do, remembering back that solids and liquids do not impact equilibrium. Water's a liquid. I can completely take out this one column from my table. It's not going to impact what we're doing. All right, I'm going to go back to filling in what I know. The initial concentration of the carbon dioxide gas is 0.02 molar and no H2CO3 or carbonic acid. Next, what we want to do is we want to say, what do we know? Okay, well, I'm going to gain product and I'm going to lose reactant. How much? I don't know. Let's call it X. That means that at equilibrium, my concentration of carbon dioxide will be 0.02 minus X, and my concentration of the H2CO3 is going to be X, because 0 plus X is X. Now I can fill in my equilibrium expression, just like we've been doing. Concentration of the products on the top, concentration of reactants on the bottom, ignoring water because it's a liquid. And now I actually know what this is equal to. We're told the equilibrium constant is 0.13. So let's plug in our equilibrium line, just like we've been doing. X over 0.02 minus X equals 0.13. Now, just like in algebra, we're going to solve for X. How do I solve for X? Well, first thing I need to do is get X out of the denominator. So I'll multiply both sides by 0.02 minus X. So I get X is equal to 0.0026, that's 0.02 times 0.13, minus 0.13X. Now I want to get all of my X's on one side. And so what I want to do here is I'm going to add 0.13x to both sides. And so I have 1x plus 0.13x, so I get 1.13x is equal to 0.0026. Now, how do I get x by itself? Divide both sides by 1.13. X is equal to 0.0023. So now what does this tell me? Well, if I take X and plug it into my equilibrium concentrations, I can find what they're equal. H2CO3 was just X. So X is 0.0023 molar. CO2 was 0.02 minus X. X is 0.0023. And so 0.02 minus 0.0023 is 0.0177 molar. So by knowing the equilibrium expression and by putting X in for what we don't know, we can actually go ahead and figure out the equilibrium concentrations given the information we were provided. All right, I hope this helped, and good luck working on your 11.3 worksheet.